If you take a perfect circle and measure its circumference, the distance all the way around, and divide it by its diameter, you get a specific number. It doesn't matter if that circle is the size of a coin or the size of a planet. If the perimeter is unrolled and laid across the center, it will always fit exactly 3 times, with a tiny stubborn fraction left over, 3.14159. But that calculation relies on a physical assumption. It assumes you are drawing and measuring this circle on a perfectly flat, unbent two-dimensional surface. In our everyday environment, pi serves as the stable conversion factor that translates the width of a round object into its boundary. You would expect a number defined by circles to stay in geometry class, but pi routinely appears in equations that have nothing to do with round shapes. This is Buffon's needle, a classic probability puzzle. If you drop a handful of straight needles onto a floor made of parallel wooden boards, the probability of a needle crossing a line is dictated entirely by pi. We find that same ratio determining the time it takes for a simple pendulum to swing through its cycle. It also appears in structural engineering, defining the maximum pressure a straight steel column can take before it buckles. Even in the Mandelbrot set, a fractal built on the imaginary numbers of chaos theory, the behavior of its boundary points converges onto 3.14. A simple two-dimensional ratio for a ring acts as a hidden rulebook governing probability, classical mechanics, and the boundaries of chaos. The reason this number is so difficult to pin down comes down to its mathematical anatomy. In 1768, Johann Lambert proved that pi is an irrational number, meaning it can never be expressed as a simple fraction. Because it is irrational, its decimal expansion goes on forever. You can calculate it to trillions of digits, and it will never fall into a repeating pattern. If you look deep into that sequence, you find strange coincidences. Physicist Richard Feynman joked about memorizing pi to the 762nd decimal place. There, in a string of random digits, you suddenly hit 6 consecutive nines. In 1882, Ferdinand von Lindemann proved pi is also transcendental. It isn't the solution to any standard algebraic equation. This definitively proved that squaring the circle, drawing a square with the exact area of a circle using only a compass and straightedge, is physically impossible. Pi is a permanent enigma, a value that is impossible to write down fully or perfectly construct. Archimedes originally tried to calculate pi by trapping a circle inside physical polygons. By doubling the sides of the shape, he squeezed the circle closer and closer, using a 96-sided polygon to estimate its true boundary. But physical geometry eventually hit a wall. To get more precision, mathematicians had to move beyond drawing shapes and invent infinite series, long chains of fractions that zero in on the value without ever sketching a curve. This transition allowed pi to bridge the gap between real-world measurements and the abstract rules of complex analysis. Euler's identity shows this connection in action. It is an equation where pi links the geometry of circles directly to the behavior of imaginary numbers. The simple desire to measure the edge of a wheel forced us to build a mathematical framework capable of describing things that never end. Let's bring this out of abstract equations and back into the physical universe. If pi relies on the assumption of a flat surface, what happens if you draw a circle where space itself is severely warped? If you measured a circle near the gravity of a black hole, the ratio of circumference to diameter would not be 3.14159. Intense mass bends the literal diameter of the circle, stretching it through curved space and breaking the standard geometric conversion factor. On Earth, our circles resolve to 3.14 because the gravity here is relatively weak. This consistent ratio serves as a local measurement, showing that we live in a region of the universe that is remarkably close to being perfectly flat. There is a modern debate among mathematicians about whether we have chosen the wrong constant to define the circle. This diagram shows the argument for tau. If you define the constant as the circumference divided by the radius, you get a value exactly twice as large as pi, which some theorists argue creates much cleaner equations. But whether you use pi or tau, the dispute is only about notation. The underlying mathematical laws governing the shape remain unaltered. Pi functions as a bridge between the probability of falling needles, the limits of infinite calculus, and the physical structure of spacetime. Every circle holds a contradiction, a simple shape we can easily draw, defined by a value that can never be fully written down.